Welcome back. In this section, we are going to learn about Frank-Starling, and which are two people, and they have what can be often is called by various names, such as the Frank-Starling law, or the Frank-Starling principle, or the Frank-Starling curve. So I just wanted you to know the name for in case you read about it in your textbook or anywhere else, you know that we've already covered this material. So the Frank-Starling law basically says the amount of blood that the ventricle ejects in a contraction depends upon the volume present in the ventricle at the end of ventricular diastole. This is what we just covered in the previous section. So there's nothing new there. This is just put to graphics now. So if we remember that cardiac muscle operates usually only on the ascending limb of the systolic curve, then we can see that there is a relationship between the length and the tension generated in the cardiac muscle cells, and that our stroke volume and later on something we'll know as cardiac output directly correlate then with this left ventricular end diastolic volume. And so because we say the end diastolic volume has to do with what's coming into the heart or the preload, then we can say the end diastolic volume correlates with the venous return to the heart. And so the net result of putting all these steps together is that Frank-Starling shows that the stroke volume and thus the cardiac output are proportional to the venous return, which is related to venous pressure. So if we look at contractility and stroke volume, the gray area is the normal working range. And so normally with a normal contraction, we are on this upslope. If we increase the contractility, we are shifting the entire curve upward. And if we decrease the contractility, then we are depressing the entire curve. So what that means is the x-axis is the end diastolic volume or the preload, and the y-axis is the stroke volume, also the cardiac output, but we don't know what cardiac output is yet. So increasing in contractility shifts our curve upward, increasing the decreasing the afterload is going to shift it downward, which is what this second graph is going to show you. So this second graph is looking at left ventricular end diastolic pressure, and on the x-axis and on the y-axis stroke volume. And what it shows is if we decrease the afterload, if we decrease the resistance for the ventricles to get rid of their pressure, then we increase the stroke volume by shifting the curve upward from A to B. But if we increase the resistance, as evidenced by increasing the systolic blood pressure or increasing the afterload, then we are depressing the curve, sending it down and to the right, as in from A to C. So what that tells us, there's a lot of variability in myocardial contractility as far as how much blood leaves with each heartbeat. In the peach colored is our normal at rest curve. In the red above it is what happens with normal exercise. And then in purple, what happens when the heart starts failing no matter what the cause, and if it depresses to the point of the green curve, you are in a downward spiral, which will lead to death. So take a minute and look at this slide. We have two different graphs superimposed on each other. In red is cardiac output. For now, just switch those words to stroke volume, and you can see the effects of contractility on stroke volume. And in blue, we have blood volume, which is our venous return. And this black dot right here is where the heart normally operates, which is when venous return is exactly the same as stroke volume exiting. And so what you will see as you change one factor or the other factor, you can see where the intersections happen among these blue and red curves. So definitely take a minute and play with this and make sure you understand this concept of Frank-Starling and stroke volume and venous return and everything we've talked about so far. Thank you for all your effort in this class. We really appreciate it.